Hi Calculus 3 class. This is the second part of the exercise of the section 1.11.11, Taylor Polynomials. In that part of the exercise, we're going to continue the previous part. We saw that the third Taylor polynomial of x ln of x is this. Okay, and we also saw that the third derivative, we did like a couple of first derivatives, was -1 over x squared. Now we're gonna estimate the error in using f of x equals t3 of x on the interval from 0.5 to 1.5. Sub-question, should we use Taylor's inequality or Lagrange's form of the remainder to do it? And the difference is actually, so in both cases, the error will be bounded by this, where m is the maximal value of the maximal value of the absolute value of the n+1 derivative at some point inside the interval. Now the difference between Taylor's inequality and Lagrange's form of the remainder is that for Taylor's inequality, this variable z right here is in the interval centered at c of radius x minus c. So it could be anywhere here, but also anywhere here. Okay? So this is like the z-axis, and x is one of these two values. We just don't know which one. Sometimes it's below c, sometimes it's after c. For Lagrange's form of the remainder, what it says is that the error is computed the exact same way, but the z is simply a value that is between x and c. So if x is below c, you only count half of the interval. You only count the values that are between x and c. And if x is after c, same thing. You only count half of the interval. You only count the part of the interval that is after c. Okay? So you always want to use Lagrange's form of the remainder, if possible, because it simply provides a better estimate. However, sometimes you cannot do it, because in this case, we want the approximation to be valid in the full interval. So you need to be conservative and use Taylor's inequality. Okay, so that's the first question answer. We have to use Taylor's inequality. So now, let's get going with that. So let's actually write down that we're going to use Taylor's inequality. Okay. There are several things to consider. The first one is that normally when you choose x, it depends on what is the value at which you're doing the approximation. But now, since you want the approximation to be valid inside this interval, so x minus c, you have to take the maximal possible value for x minus c. So let's actually write that down. Since we want the approximation to be valid on the interval, so for x, so in other words, like x has to be between 0.5 and 1.5. We have to consider the largest possible value for x minus c. So we consider the largest possible value for x minus c. And regardless, this largest value automatically occurs at the endpoints. So it will happen at it happens at endpoints. Okay. So this means that x minus c, okay, is going to be smaller or equal than 1.5 minus 1. That's the value of c, right? Okay, so yeah, well, that's it, exactly. So it's going to be smaller or equal than this, which means it's going to be smaller or equal than 0.5. Okay, Let's keep this in mind. Then we have to calculate m. We have to calculate the maximal value of the fourth derivative. So what it means is that, so let's calculate m. Okay, well, we need to take a fourth derivative for that. The fourth derivative of x. In this case, it's going to be 2 over x to the power of 3. Okay, so simple power rule. That's going to be the fourth derivative. So now we have to ask, where is the maximum of this derivative? As you can see, it happens when x is as low as possible. So the max happens at the lowest possible x. Okay. So in this case, it will happen when x is equal to 0.5. So when x is equal to 0.5. So now we can erase like this part. We're going to finish the problem here. So what does it mean? It means that m is equal to, so it's the max of this, but that will be 2 over, let's put the absolute values for now just to be safe. So it's the absolute value of 2 over 0.5 to the power of 3. And this is easy to calculate because this is exactly 1/2. So it gives us 2 to the power of 4. Okay. And now we can use Taylor's inequality, which bounds the error by this thing. So the error, so that would be like step number 1, let's say. It's to determine which value of x do you consider. Step number 2 would be to calculate the m. And step number 3 is to plug everything in. So the error is smaller or equal than m. So m is 2 to the power of 4. X minus c. So actually, let's put a little bit of colors, right? So this is the m, okay? 2 to the power of 4. And this, so we saw that x minus c, its largest possible value is 0.5. So we're going to put here, instead of this, we're going to put 0.5 to the power of 4 because n plus 1 is equal to 4. Okay? So just take note here that n plus 1 is equal to 4. Okay? And now we're going to divide by n plus 1 factorial. So 4 factorial. And now the funny thing, as you can see, is that, so I need to push this a little bit. So note that n plus 1 is equal to 4. Okay? And the funny thing, as you can see, is that the green and the orange cancel exactly because this is 2 to the power of 4 and this is 1/2 to the power of 4. So the error will be 1 over 4 factorial, which is 1 over 24. So 4 times 3 times 2, 4 times 6, 24. So that is the maximal error. Okay, so in the last video, what we're going to see is, can we use the alternate series theorem, estimation theorem, in order to solve the problem and to get a better estimate? See you there.